So, that is what we are saying, purpose of ventilation is threefold. Purpose of ventilation are actually threefolds: hygienic ventilation, air changes, right, and removal of heat, and comfort ventilation. So, this is given, hygienic ventilation is given based on what? This is the amount of carbon dioxide, this is the carbon dioxide, this is the amount of carbon dioxide, exhaled by every adult, and this is the atmospheric carbon dioxide. Typically 0.4% is a carbon dioxide in atmosphere, right. So, how much you got to remove will depend upon number of persons. So, in a restaurant a large number of people will be sitting at one go. I mean, we are talking about not the open air type, the closed scenario. So, number of people will be sitting together. So, the cafe you can see that is 12 minus 12 I mean 12 to 15, sorry, 12 to 15, 12 to 15, and general habitable building 3 to 6 air changes. We understand of course what is air changes. This is the minimum required. Cinema is higher, kitchen is higher, because kitchen you also got to remove the gases, gases coming out of the cooking, even cooking, the food, oil, etc., etc. So, the smoke that comes out. So, therefore, this is the basis. This is given in code, this is given in code, one can calculate this out roughly. Now, how much is, if it is for removal of heat, then how much sensible heat is to be removed? If it is known, then required air changes I can find out. We said that, if you remember, we said 13 N V, that is equals to C B approximately, and delta T. So, if I know V in meter cube or NU I want to find out, or if the sensible heat to be removed is actually CB dt, sensible heat, this is equals to QS, which can be written as approximately 1/3 or slightly more accurate is 2.97 into CB is a rate of ventilation. If I express it as number of air changes into volume of the room, but if it is in meter cube per second, if we go back to our original equation, it was we how did you get this CV? Basically we said N is the number of air changes per hour, V is the volume of the room, right. So, this is, if I want to convert this into meter cube, this is per hour, this should be divided by N is the number of air changes per hour. So, meter cube, this is in meter cube, this is that many meter cube per hour, that many meter cube per hour. This divided by 3600 will give me per second. So, that would give me meter cube per second. So, 1/3 like based on this basically. So, CB, if the sensible heat I want to remove is known, the per degree if I know it, or if I know the temperature difference, then I can calculate out how much QS or meter cube per second flow rate, how much it should be based on this, right. So, if I know this, if I know QS, amount of heat I got to be removed, QS is equals to V delta T divided by 1/3. So, this should be in this, what is this, in meter cube per hour, then the required N air changes, N. So, this basically this is what we are saying is CV delta T is equals to QS, and CV is roughly about 1/3 N into V. So, N into V delta T is equals to QS. So, I want to find out N number of air changes, that will be simply 3 Qs divided by delta T, where is the volume of the room must be coming somewhere, the volume of the room should have come here, delta T has come, together with this it should be volume, per meter cube of the, it should be per number of air changes can be found out from ventilation from this one, sensible heat, and this is per meter cube of the room volume actually. This will come out to be per meter cube of the rate of ventilation per meter cube of the room volume, or you can anyway we can calculate out simply from this one how much meter cube per second I want to find out, even that I can find out, because this is what I will be using later on. So, I can easily find out sensible heat, how much, depending upon how much sensible heat I got to remove, what is the number of air changes I require, I can find out. Number of air changes depends upon, depending upon how much. So, if I am my ventilation design will be based on, ventilation design means the required N or meter cube per second. So, I can convert it into meter cube per second and find out. Now, Qs is equals to mc delta T, okay. So, rho Cv delta T, mass into volume into delta T, volume of the room. Rho can be actually, now I can do a little bit of more complication on rho. Earlier we take roughly around one, that we took 1300, rho C we took 1300, remember, and then we said 1300 by 3600. I want to take a little bit more elaborate, then we know at 20 degree centigrade rho is 1.2 kg per meter cube. At any other temperature it will be 1.2 divided by 1.273 plus 20, divided by 273 plus T multiplied, because rho and T, rho into T, rho 1 T1 must be equals to, that is right. So, 273 plus 20 is the temperature corresponding to 1.2 divided, this will give a rho at any temperature. So, this is 1.02 is the C taken delta T into V. So, 1.1 on average C is taken as this. So, you can complicate it a little bit more and find it out the V instead of taking a constant rho or 1/3, that 1/3 equation, we can make it a little bit more complicated. Also, you can find out how much latent heat I have to remove. So, if I know the sensible heat I want to remove, by using the formula that we have used, we can find out how much meter cube per second I got to remove. And here I can be more accurate using the density rather than simply 1/3 NB. I can use rho as depending upon the temperature, average temperature, and C as 1.024 kilojoules per kg, as we have seen. I can also find out how much latent heat I want to remove, because you see it is not only the carbon dioxide, but also the vapor, moisture vapor generating out of the sweat, etc., also through our respiration process. Besides, if there is a process, let us say if I have a kitchen and I have hot food, I am serving hot food. So, moisture will evaporate from the food itself, and cooking is usually boiling through water. So, there could be some evaporation occurring, and I got to remove those moisture also. Some cases latent heat removal is important. In any case, latent heat removal will be there. Supposing air comes, a dry air comes from outside, it will absorb moisture from the room also, irrespective of whether you have designed it for or not. So, latent heat has to be removed. You can find out from that considerations also what is the required flow rate. What is the required flow rate? Supposing so Q ml, the amount of heat I want to remove is mass into latent heat into delta G is the difference in the moisture content of air. Dry air comes from outside, it absorbs moisture, therefore, its moisture content will change. Absolute humidity of the air inside and outside could be different. So, if it is inside, if it comes and absorbs moisture, then it goes out together with the moisture, it actually also carrying the latent heat of evaporation, because latent heat of evaporation is also being removed. So, the dry air comes, it absorbs moisture. If it is in liquid form, then it has to be vaporized. So, where from the heat will come? It will come from inside itself. So, this is the latent heat removal, mass into latent heat into delta G, and mass will be rho into volume of the room, rho into volume of the room. So, using that partial vapor pressure equation, which I think I have given you earlier, applies both dry air as well as vapor, and we know that PA, VA, etc., this we looked into earlier, PV, etc., this we looked into earlier, right in the beginning we have looked into, and from this one can actually find out the moisture content as 0.6 to 0.622 partial vapor, pressure vapor, and pressure of air. So, from that we can, G is the moisture content we can relate to. Therefore, QL 1.2 is the density. This is the temperature at 20 degrees centigrade when it is 1.2. At my temperature, this is the density into V into delta G. And how will you find out delta G? From partial vapor pressure outside and inside, because using this formula, right. So, delta G and L is the latent heat. So, this comes out to be 352, this multiplied by 1.2 is 352 into V is the volume of the room. If I am looking at or flow directly, I can look into flow, 622 into vapor pressure difference between outside and inside, delta PB divided by PA into L. So, from this I can find out again V, if I know how much latent heat is to be removed, how much latent heat is to be removed, how much moisture vapor is present inside the room, and correspondingly how much latent heat removal is possible, that if I know, from that I can find out the V required. So, G this we have seen, and then therefore, V is nothing but some constant QL PA delta PB by L from this equation. Simply V is expressed from this one, V is equals to QL. So, QL by L PA divided by delta PB QF, so this was V is QL by L PA divided by delta PB into all rest of the things are all constant. So, it will be delta, this PB can be expressed in terms of mercury height of mercury or head of mercury. So, delta Hg vapor pressure can be expressed in terms of mercury head. Pa is atmospheric pressure in Pascal, L is 2510. So, one can get an expression for PV is equals to rho of mercury Hg G delta Hg, that is what is the PV, because it is a head difference of mercury head difference, manometric head difference of vapor pressure outside and inside. So, therefore, PV can be expressed in this manner, and if you do that, it will give you delta Hg is allowable vapor pressure difference in millimeter of mercury, and from this you can calculate out the V values. From this you can calculate out the V. From this you can calculate out the V. C is the constant. C is a constant which will depend upon all these factors that we looked into, and from this you can find out what is the V required. So, whichever is higher V, you choose that. Whichever is higher V, whether V latent heat removal or V for sensible heat removal. Sensible heat will come from where? Temperature difference. Cv into delta T is equals to Qs. So, if I know how much heat I want to remove, sensible heat I want to remove, some cases latent heat may be generated, removal might become more important through ventilation, right. Usually that is not the case. Usually latent heat to be removed is less, but supposing lot of vaporization is occurring inside kitchen or something like that, right, or some processes, not kitchen even, some processes where lot of moisture is evaporating all the time. So, you got to remove that heat generated through evaporation, then latent heat might become a dominant factor, and quantity of ventilation required you can find out, because latent heat you want to remove QL is equals to the flow multiplied by the rho into L, right. So, into delta G, or basically delta G is the moisture content difference, how much moisture vapor is generated, that is moisture moisture content difference. Now, moisture content difference can again be expressed in terms of partial pressures. Moisture content can be expressed in terms of partial pressure, atmospheric pressure and partial pressure difference between outside and inside through the formula that I have given you. And if you convert them into head of Mercury, so delta Hg, all are constants except this part of the formula that we have seen, this part of the formula C dash. So, V can be obtained from this equation if you know how much QL latent heat to remove in processes. But usually this will not be large, usually in habitable rooms, residences, etc. This will be small. Whichever is small, you ignore it. Whichever is higher, out of meter cube per second or number of air changes you found out for latent heat transfer or sensible heat removal. Whichever is higher, you choose that, because that will ensure automatically the other one is satisfied. So, either VL or VS, as we have calculated, like VS we have calculated in VL we calculated from this formula, whichever is higher, VS we calculate from this formula. So, whichever is higher, that you choose, and that is what is good enough for our purpose for natural ventilation. So, that is what it is, that is what it is. So, first is you find out whichever is greater. So, this is related to removal of heat. Minimum is hygienic ventilation, that you have to provide in any case. If this value is higher than hygienic ventilation required, then obviously you will provide, and this is usually higher, right. If you want to ensure some heat removal also, then it has to be higher. So, whichever is higher, you would be choosing them. And then what are the forces? Velocity aspect we are coming later on, that is slightly differently looked into. But today you have got, actually if you want to go in a full analysis of a large building, large space, naturally ventilated or ventilated otherwise, you have CFD models solving robust equations actually. But this is simple principle I am talking of. In this class we are talking of simple principle. You want to use it in a large building, then possibly computational fluid dynamics models one can utilize. Otherwise, largely is based on empirical results. The velocity calculation, we will come to that sometime later. So, okay, the principle wise driving force, what are the driving force for ventilation? Driving force for ventilation are either wind, or it can be driven by thermal gradient also. That is what we have seen when we are looking at wind tower. So, this is what we call a stack effect. This we call a stack effect, and wind driven is what is the common. Wind driven is what is the common one, right. So, wind driven is a common one, and you would have calculated as when you have done design for wind load, pressure on a surface, right. So, from it would come out from Bernoulli's equation, actually pressure is half rho V square and is 0.3613 V square corresponding to, right. So, what we see is velocity, wind velocity, if it is V, then pressure is proportional to delta P to the power 0.5, right. So, V is proportional to delta P to the power 0.5, and flow is velocity multiplied by the area. So, meter cube per second flow would be proportional to A into delta P, right. But if I have a window or opening, I have some window or opening, it will offer some sort of resistance to flow. So, that I am calling as R. So, the if it is wind driven, the flow meter cube per second or NV is a function of area of the opening, function of pressure difference between these two sides, and of course a resistance factor divided by resistance, because this there will be stream flow, even if you assume stream flow, the flows there will be Venturi sort of effect, and it would actually there will be a resistance offered, it is not free flow, right. So, this is R takes care of that. So, R is a resistance, right. This we have seen velocity as a function of height. Remember this we talked about when we were talking about climatic parameters, we mentioned gradient height, and you can see that this is in open country, this is in city center, and this is in suburban. If you remember, I think I might have shown you this diagram or may not have shown. So, delta P is something like this, velocity delta P or velocity both changes, velocity changes. So, delta p would also change depending upon where you are. Open country, near the ground it would be, yeah, it is very small, or near T 0, boundary layer effect would be 0, it would be 0 actually. So, height of the building, it depends upon height of the building. So, delta p is a function of height, and if I want to find out delta p around just about an opening, then I must find out the wind flow pattern around the building, because the pressure I have let us say I have this building, right, building, I have this building, let us say this is the building I am looking at. Now, wind direction is this, at the moment let us assume it is normal. So, it will get stuck here, it will be obstructed. So, there will be excess pressure here, right, and it would flow in this manner. There will be a partial vacuum here, a suction or partial vacuum here. So, on the windward side you will have excess pressure, on the leeward side you will have partial vacuum or suction. So, that results in the flow through the building itself, that results in flow through the building itself. In plan, if I look at a square plan, let us say, so this here I will have excess pressure, some suction here as well and some suction there forming eddies. So, that is how it is. So, wind flow pattern around the building, what we have seen so far, flow is proportional to delta p to the power 0.5, it is a function of area and divided by resistance of course, and then around in a building windward direction you will have excess pressure, on the leeward side you will have suction. So, that creates the pressure difference delta p over the whole building, but inside there will be some pressure, outside there will be more pressure in this case, and here there is less pressure because suction and slightly higher. So, if you have windows here and windows there, it would actually result in cross ventilation or flow of air through the room space or building space inside the building. So, that is how, that is what it is. So, you can see different types of curved roof, they look like this, flat roof, they look like this. If it is at 45-degree angle, then you will have possibly excess pressure somewhere there, suction there, suction there. If it is something like this, there will be suction here and partial some suction plan L shaped. So, depending upon shape of the building and direction of the wind, you will have some windward areas and some leeward areas. Leeward areas are the areas where you will have suction, and there are other areas which will have high pressure on them. So, you will have high pressure and high suction on some other places. So, that results in delta p and that results in flow. Now, if you have two buildings in series, right. So, you see this flow through this should be, it would be suction here actually, but if the distance is sufficiently large, then there will be that there can be excess pressure here as well. If I have an opening, the velocity will increase there, Venturi effect, right. If I have an opening, Venturi effect, I will have velocity, higher velocity. So, corner stream will go like this, corner stream will go like this and so on. So, this for example, between two buildings I may have channel flow, high flow around. So, while planning the building, one can keep this kind of these aspects in mind. As I said that all these issues related to environmental design of building as we call it, so thermal design, acoustics, ventilation, daylighting, fire, almost all of them, leaving the of course services part of it, for example, lift design of lift or plumbing system, they may not be dictated by my urban planning, but they have some role there also in urban planning, because your water supply system from the main municipal thing, it would depend upon that, right. So, urban planning dictates this and you cannot keep them away. This is ignored at times, but bylaws are supposed to take care of them, So, this it starts all from urban planning. For example, two buildings, if they are too close, it can simply block. So, spacing between the building is very important, right. Generally, if you have 6 times the height of the building, you will not have any shadow effect. Like this one had some shadow effect. In fact, you have suction here, and this one is driving the wind flow pattern like this. So, if it is too close, you might have some suction here, although the top portion will receive some, it will receive the direct wind. But if the tall building is on the other side or wind direction is from this side, then actually this will not, this will be totally shadowed. So, this is spacing is 6 times the height to avoid shadow effect. Height of the taller one, in fact, if they are different height of the taller one, depending upon wind direction, right, the one in the windward side 6 times the height of that one at least it should be. Better would be something like this, stagger it. For example, this is the wind direction, better would be stagger it, right, stagger it. So, this could be 3H, this could be 3H, this could be 3H again, depending upon wind direction. So, you can actually, this sort of concept can be kept in mind while doing urban planning, right. Okay. So, what we have looked into, basically the purpose of ventilation. We said there are 3: hygienic ventilation, ventilation for removal of heat. Third aspect is comfort ventilation, very close to the skin velocity, which I have not discussed so far. Then we looked into for thermal ventilation, for removal of heat, how much quantity I should select, quantity of flow that I should be using in design, how much meter cube per second or how many air changes. That we can find out from latent heat to be removed or sensible heat to be removed. Usually sensible heat to be removed is higher. Whichever is higher, you choose that. Usually most of the spaces sensible heat will be higher, and sensible heat removal or latent heat removal, whichever is higher, you choose that, and from that, that's how you find out quantity of air flow rate you require. Now, to ensure that that much air flow rate takes place, I got to know the driving forces, and we identified 2 driving forces. One is the wind, other is the thermal, and we have looked into the wind flow pattern around the building, which are important from urban design point of view, the spacing, and we have also seen that the flow is a function of the area of the opening, pressure difference, and obviously a resistance factor which will depend upon shape, etc. But then we have all regular rectangular shape windows. Now, to identify delta P, or where I will have excess pressure and where I will have suction, I must understand the pressure distribution around a building. This is of course visualization. CFD can give you those ideas pretty easily, but if you know that. So, but visualization is something like this. Visualization is something like this. So, now let us look at how does pressure is distributed, how pressure distribution occurs within around a space or around a building. So, as I said, depending upon the direction of the wind, so if you consider this 45-degree angle. Now, one thing I would like to highlight, we do not consider again in details like normal wind, 5-degree incident wind, 10-degree, we do not do that, because actually wind direction keeps on changing. It is not worthwhile going into so much accurate calculations. So, what we do, we consider mostly 2 cases, normal 45-degree angle, right. It is not worthwhile going into so much of details. So, normal or 45-degree angle, at best sometimes 30-degree, 60-degree, 90, but even not that, usually 45. So, you can see that normal wind and 45-degree wind we are considering. 45-degree wind, you will have excess pressure here, negative pressure here, negative pressure here. Normal wind, positive pressure here, negative pressure here, some negative suction, they will vary in this manner. So, that is how it is, right. And that is another diagram showing the direction of the wind and suction, etc., etc. This one should be able to, one should be able to visualize. This for L-shaped building, normal, the suction somewhere there and suction, and if the wind direction is 45 degree, suction some, depending upon the wind direction, something like this from this side, sorry, you will have excess pressure here and some pressure here, then suction, and so on. So, that is how one will have, wind on phase B and A separately shown. So, one should be able to visualize this aspect, that where is your, if you are manually looking at it, or to want to locate your windows, you should locate your windows in such a manner. I am talking of unconditioned building, maybe single story or similar sort of situation. You locate your windows where there is excess pressure first of all, and some windows you should be locating on the suction side also, leeward side also, because then only you will have delta P flow. So, that is what pressure distribution, look at it in this way. So, natural ventilation, well, if I calculate out, this I suppose I have, because we said velocity is proportional to under root delta P to the power 0.5. There is a constant of proportionality. There is a constant of proportionality, and how much this would be? Because P was related to delta P was related to 0.6 V square was equals to. So, delta P should be, it should be 0.6, if that was delta P, if the delta P is 0.6 V square. So, 1 by 0.6 root over, from that it must be coming, it is coming there, coming from there, and the R also is involved, also R is involved. So, I do not have this values derivation, but this 0.827, because it would be, yeah. So, then together with that would come as multiplying by R should come as, I mean divided by R, that would come as 0.827. So, this is B can be related to, B can be related to delta P to the power half 0.827 into A. V is delta P to the power half, right, and delta P was 0.6 V square. So, this is 1 by 0.6, right, under root 0.6. How much is that? So, this is what we take for granted for our purpose, that V is equals to around 0.827 A into delta P to the power 0.5. Now, for openings in parallel, supposing I have got one opening here, another opening there, this is my room. Well, this side I do not talk about. Two openings in parallel, and here is, let us say, delta P exists between this point and this point. So, there will be flow, and this then this would be A1, let us say this is A2, delta P is same across these two, delta P is same across. So, delta P to the power 5 is same across. So, total flow will be equals to 0.827 A1 plus A2 into delta P to the power 0.5. You can sum up the areas, but if I have another window there, I will have delta P1 here and delta P different pressure there, right. So, let us see. So, if when they are in series, things are, so for parallel openings, V is the sum of all openings and pressure difference. So, therefore, I can write V is sigma A. For in the same wall, as many number of openings I have, I can simply sum up, right. Or for that matter, because in a room I will have pressure difference across the all windward side where there is excess pressure outside, delta P will be by and large same. So, for all windward located windows, sigma A will be sum of all the areas of all windward located windows, right. For openings in series, flow is same, pressure difference is different, because whatever is coming in must be going out. So, one window here and one window there, whatever comes in will go through. So, flow is same, but delta P's are different, right. So, it is nothing but series equation. So, delta P1 is equals to the flow divided by area, because it was this one. So, delta P1 I can find out delta P1 is the first one. So, if I know the flow here 0.827 A1, from this one I find out, and delta P2 similarly same flow, but A2, right, same flow A2. So, delta P2 same flow A2, same flow A2, delta P2 will be this. This is suction and then inside is still high. So, one window and another window in the cross ventilation, if I am talking of. One window on the windward side, another window on the leeward side. So, inside pressure and the outside pressure and inside pressure, the two pressure differences, right. So, delta P2 is something like this, delta P2 is something like this. So, then I can sum up delta P1 plus delta P2 and it will be given as V by 0.87, it follows from there only. It follows from there only, delta P2, delta P1, V square I can take it out, V by 0.827 I can take out. So, I will have 1 A1 square plus 1 by A2 square, right, and therefore, V can be written in this manner. Delta P1, I just square it up, I mean take under root of everything. So, this is 0.5 and then 827 goes there, divided by this one to the power 0.5, because this one to the power 0.5, right, 0.827 multiplied by 0.827 divided by this whole thing to the power 0.5. So, if it's equivalent to, it's therefore considering the inlet area, so it is basically equivalent area is given as equivalent area, then we can find out. Supposing my equivalent area, inlet area is A, outlet area is A, both are equal, let us say, then if they are equal, then 1 by A square plus 1 by A square to the power 0.5 is equals to this. So, root over 2A. So, actually equivalent area for inlet and outlet being area being different, I can find out from this formula. I can find out from this formula. In this case, like 1 by root over root 2 by A is equals to 1 by A1 square. In other words, if I square up both the sides, I will get 2 by A is equals to 1 by A1 square plus 1 by A2 square, A2 square. So, V can be written as pressure difference, total pressure difference existing between outside, in windward side, sum of the pressure differences actually windward side minus the inside, and then inside difference between all of them, sum to the power 0.5 anyway comes in, into the area is equivalent area is A. So, V is equals to A, 0.827 anyway remains, and delta P 1 plus delta P 2 to the power 0.5, to the power 0.5, to the power 0.5. In other words, I can consider the equivalent areas as by using this formula. Equivalent area of inlet and outlet I can find out by this formula, right. So, I think we will just stop here and then putting everything into account we can actually get an expression. We will look into this in the next class.